To obtain an expression for the energy stored in a capacitor, let us consider a parallel plate capacitor having metal plates X and Y, each of area A and separated by a distance D. When the plates X and Y of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q and the other is given a charge minus Q. The plates X and Y are connected to the positive and the negative terminals of the battery, respectively. Let the capacitance of the capacitor be C, which is a constant. Let us now try to understand the mechanism involved in the process of charging of the capacitor plates from an energy point of view. In order to do that, we need to first imagine that the plates of the capacitor are completely uncharged. Now imagine removing infinitesimally small positive charge plus dq dash from the plate Y and transferring it to the other plate repeatedly. In this process, we see that the plate Y is getting negatively charged due to the buildup of excess negative charge on it, and hence the plate Y is at a lower potential. Simultaneously, we see that the plate X is getting positively charged due to the buildup of excess positive charge on it, and hence the plate X is at a higher potential. Therefore, the process involves transferring charge from the plate Y at the lower potential to the plate X at the higher potential. The electric field that builds up between the plates has a direction that tends to oppose further charge transfer. In other words, we can say that there exists a force that repels the transfer of charge plus dq dash repeatedly to plate X. Therefore, as charge accumulates on plate X, this repulsive force on the charges being transferred increases, and hence the amount of work done to transfer charge also increases. This work is actually done by the battery at the expense of its stored chemical energy. The work done to charge a capacitor is stored as electrostatic potential energy, U, in the capacitor. Now, let us consider a state of the capacitor where the charge on the plates of the capacitor is Q dash and the potential difference between the plates of the capacitor is V dash. Then, Q dash is equal to CV dash or V dash is equal to Q dash by C. Let this be equation 1. Now let us transfer the next additional charge plus dq dash to the plate X of the capacitor from the plate Y and let the work done in the process be dW. From the definition of potential difference, we know that V is equal to dW by dQ. Therefore, dW equal to V dash dQ dash. Let this be equation 2. Substituting equation 1 in 2, we get dW is equal to Q dash by C into dQ dash. Let this be equation 3. Now, let us calculate the total work done W to charge the capacitor from 0 to a total charge plus Q. We know that W is equal to integral dW in the limits 0 to plus Q. Substituting the value of dW from equation 3 in the above expression and simplifying further, we get W is equal to Q square by 2C. This work done, W, is stored as electrostatic potential energy in the capacitor. electrostatic potential energy of the capacitor is denoted by U. Hence, we get U is equal to Q square by 2C. Using Q equal to CV, we also see that energy stored U is equal to Q square by 2C is also equal to half CV square. Now, since Q is equal to CV, U is equal to half QV. A charged capacitor is analogous to a stretched spring. When the spring is stretched, it stores elastic potential energy U equal to half kx square, where k is the force constant of the spring and x is the elongation in the spring. When released, the spring loses the stored elastic potential energy. Similarly, the capacitor, when charged, stores electrostatic potential energy U equal to Q square by 2C. We see that the value of Q is analogous to the elongation x, and the value of 1 by C is analogous to the value of the force constant K. The energy supplied to the capacitor in the charging process is released when the capacitor discharges. We can also say that the energy stored in the capacitor is localized in the electric field between the plates. Now let us derive an expression to calculate the energy density of the region between the plates of the capacitor. The electric field strength E between the plates of the capacitor is equal to V by D, assuming a uniform electric field between the plates. Let this be equation 4. The electric field fills the region between the plates, and this region has a volume E equal to area A into distance D. The energy density is defined as energy stored per unit volume. Therefore, energy density is equal to the energy stored by volume. This is equal to half CV square divided by AD, since the volume is equal to AD, which is equal to CV square by 2AD. Multiplying and dividing the right-hand side of this expression with D, we get energy density is equal to half CD into V square by AD square. Let this be equation 5. For a parallel plate capacitor, we know that the capacitance C is equal to epsilon naught A by D. Therefore, CD by A is equal to epsilon naught. Let this be equation 6. Substituting equations 6 and 4 in equation 5 and simplifying, we get energy density is equal to half epsilon naught into E square. This equation for energy density holds good for the electric field of any charge configuration in general.